No, you know what my mom said? My mom said, she's like, is that your chemistry teacher? And I was like, yeah. And then she was like, why is she teaching to herself? Because she heard nobody talk.
Right? Because nobody, well, A, nobody talks, but B, you can't really, it's kind of directional, like it doesn't pick up students' voices.
Yeah, and then she's like, oh, she's teaching to herself.
It would be, it's a fair question. That would be odd. Although I have done it. I don't like doing it, but back, yeah, during COVID, I was like, okay, here we are, friends. Okay, so here we have, how does the pH at the equivalence point change as the acid titrated becomes weaker? So as the acid becomes weaker, what happens to the pH at the equivalence point? Please tell your partner. So as the acid becomes weaker, pH at equivalence point gets?
Higher?
Higher, yes.
It can't be wrong. Chemistry's not chemistry. Oh.
So as acid becomes weaker, pH at equivalence point becomes higher. And you can see that in this graph here. We have a strong acid, and its pH at the equivalence point is at 7. And we have one that has Ka of 10 to the negative 2, and its pH is at the equivalence point is just above 7. And then we've got 10 to the negative 4 as our Ka. All right, and that one ends up there, and we have 10 to the negative 6. So our Ka is getting smaller and smaller, and the pH is getting higher and higher. Yes? Okay. Other things that change as the acid becomes weaker, the initial pH increases. And of course, the pH at the half equivalent point increases because what is pH at the half equivalent point equal to? It's equal to Ka. So you can see here, the half equivalence point would be here and here and here and here. And you can see for the one where the Ka is 10 to the negative 8, the half equivalence point is at pH 8. Yes? For the one where we have 10 to the negative 6, the half equivalence point is at pH 6. Yes? Does that make sense? Cool. 10 to the negative 4. Half equivalence is at 4. And 10 to the negative 2. Half equivalence is at pH 2. Oakley dokley. And here is a titration curve of a weak base by a strong acid. And all we really do is we take this curve and we turn it upside down. So do you see how in the weak acid we have the little hill at the beginning is an uphill hill? Yes? But when we start with a weak base, the little hill is a downhill hill. Okay, so we've got our hill. At our half equivalence point, concentration of NH3 is equal to NH4. So I guess our weak base must have been NH3, and our strong acid was HCl. So when we react the two of those, NH3 plus HCl, this is our weak base, this is our strong acid. Our products are NH4 plus Cl minus. And even though we do not get a salt plus water, this is still a what type of reaction? It's an acid and a base. It is a neutralization. It doesn't look like a lot of neutralizations because it doesn't have that hydroxide from the base. That's because this one is a weak Bronsted-Lowry base, but this is still a neutralization reaction. So you get an acid plus a base gives a salt. You just don't get any water because there was no hydroxide. Okay? Now, here is our salt. The salt is NH4Cl. And maybe I should look at what the questions are below because probably I'm going to end up writing the same thing as is in the questions. What would the initial pH be if the base in the flask, were 0.1 molar NaOH instead of 0.1 molar NH3? Go ahead, calculate it.
Oh.
Did you guys get 13? Excellent. Because NaOH dissociates completely to give hydroxide, so the concentration of hydroxide is 0.1, in other words, 10 to the negative 1. So the POH, negative log of 10 to the negative 1 is 1. And so the pH is 14 minus 1, which is 13. Why is the initial pH of NH3 lower than the initial pH of NaOH? Why is the initial pH of NH3 lower than 13? Because it is at like, I don't know, 11.2 or 11.12. What do you guys think? Because NH3 is a weak base. Yeah? Because NH3 is a weak base, therefore the same concentration of base produces less hydroxide than in a strong base. Oh, I guess I should have made you write the neutralization of NH3 by HC. I'll write it again anyway, just in case. So when we get to the equivalence point, what are the only species present? NH4 plus and this goes to completion. And at the equivalence point, these are all gone. Okay, at the equivalence point, remember, everything has been reacted and there's no excess of either. Okay, so there's no excess reactant, all reactant is gone. So the only thing left we have is product, which is NH4 plus and Cl minus. So who are the ions? This is our salt. And remember, the pH at the equivalence point depends upon hydrolysis of the salt. pH at equivalence point depends on hydrolysis of salt. Okay, so who are the ions? We have NH4 plus and Cl minus. Does NH4 plus hydrolyze? Yes, it's one of our 4 cations. And Cl minus, does it hydrolyze? No. And right off the bat, if we didn't need to do a calculation, or show an equation, you could just say, I have cationic hydrolysis. and therefore the solution will be acidic. Okay, but if you are asked to prove that, then you would probably write the equation, the hydrolysis equation. Please do that. Okay, so the pH at the equivalence point is going to be lower than 7 because the hydrolysis of the salt produces hydronium. Hydronium? Where'd that B come from? That U looked like an O. Hydronium. There we go, hydronium. Is good? Okay. So it's basically just completely the reverse of a weak acid plus a strong base. Yes? And so the greater the Kb, what can we say about the pH at the equivalence point? Actually, I should say as the Kb decreases. As the Kb of the base decreases, as the base gets weaker. As the base gets weaker, the pH at the equivalence point will decrease. Excellent. Okay. And the half equivalence point, the pH is 9.24. What does that give us as our pOH? .76? Yes. And let's just quickly let's find the Kb of NH3. Okay, can you guys find the Kb for NH3? Where should you be looking? In your book. What should you be looking up? The Ka of the conjugate acid. What? Oh, I did something wrong. Oh, that's supposed to be 14, not 4. Silly me. Now, what happens if I find the PKB? Look at that. So at the half equivalence point, the POH is equal to the PKB. Zoinks.
Yeah.
But still, pH is still equal to pKa. So both of those are true at the half equivalence point, no matter whether you are looking at the base being neutralized or whether you're looking at the weak acid being neutralized. Okay, both of those are true. So if you're like, okay, there we go. Okay, is good? All right. So you should be able to recognize that this is a weak base because it starts high and finishes low, therefore it's a base. The pH at the equivalence point is smaller than 7, so it's a weak base. It's got the little hill, so it's a weak base. And the what's the other thing? The initial pH is not what it would be if it were a strong base. It's lower. What do we call this region here? What's that region called? That's called the buffer region. Explain to your partner why that is called the buffer region.
They're trying to trying to bring the peach there, so that was space.
So some of the weak base in this section of the curve here, some of the weak base has been neutralized. I guess there should be a D on the end of neutralized to form some of the conjugate weak acid. And what do we have if we have some weak base and some of its conjugate weak acid? That is a buffer. So that's why it's called the buffer region, because you've made a buffer. Is good? Okay. Now, having done all of that, how much time in like regular chem are we actually, like how many questions are you gonna get on titration curves? It's just gonna be recognizing them. Is it weak acid, strong base? Is it strong base, strong acid? Is it, you know what I mean? Like it's just recognizing them, okay? Or explaining why the equivalence point is greater than 7 or less than 7. Not much more than that. Okay, there's some answers there. There's some exercises here. I'm going to let you do those. We are going to move on, though, to choosing an indicator, because this is the other thing that you might have to do, is to choose an indicator for an acid-base titration. Oftentimes, we use an indicator rather than a pH meter, and optimally, the indicator should change color at the pH of the equivalence point. So for this strong acid, strong base titration, in theory, we should pick something that changes pH at changes color at pH 7. And what indicator changes color at pH 7? Well, a good choice would be bromthymol blue, because it changes between pH 6.0 and 7.6. Yes? This is on page 106. So last year we titrated a strong acid with a strong base. Did we use bromthymol blue as our indicator?
Yes.
Did we? What did we use? We used phenolphthalein. Now, phenolphthalein does not change color at pH 7. Its transition point is around pH 9. Why is that? Why is it still okay to use phenolphthalein? How much volume change, how much NaOH do you have to drip in to get from pH 7 to pH 9? How much volume does it take? Like hardly anything. Yes? Maybe a half a drop? Yeah? Maybe not even that. And in fact, we should include the methyl orange as well. And that would be at about 4. All of these indicators would require the same volume to get to that end point. Yes? All of them will change color at the same volume of NaOH added. So for the weekend, you guys can do the questions in the previous one that we just did and work on your overall review, please. Okay? Our test will probably be next Friday? Friday. Next Friday. And by the previous thing, I mean 5.6b. Do the 5.6b exercises.
Right.
Yes.
George and I were wondering if we could do the test on Monday because we have a what you call it
Thursday on Thursday, and then we're council, so we have to go after school and we have to
Yeah.
stay after school.
No problem. I have no issue with that. Yep. Hi.
Please.
Yes.
No, but we're in the theater till 10. I know. Might as well be at home.
There you go. Do you have a data booklet? Do you have a data booklet? Perfect.
I want to ask, is what I've done here of any significance to
No.
chemistry whatsoever?
No.
So it's nothing. That's
No, because this guy is orange, above 6.6 and below 8.
Yeah.
Right? This guy is orange, above 5.2 and below 6.8.
Yeah.
So what pH would turn both of them orange? It has to be between that and that. Yeah? Yeah.
I've overthought it so hard.
Hi.
Question?
Yes,
Is it actually a straight line or it's like a
it's
steep?
pretty straight,
Oh,
especially with the strong acid, strong base.
I see.
But
Yeah.
in nature, you have to understand not many things are straight.
But
Very good.
you would tell what's the